Okay, ionic equations. What these are, they're kind of like the balanced equations that we've talked about before. But in this case, with ionic equations, we're really studying what's happening with the ions in each case. Okay? To give you a general idea, if I have something like sodium chloride, okay, and this is aqueous, and I react this with, say, silver nitrate, and that's aqueous, all right? What is going to happen? Now, in an ionic equation, we're going to look at this and say, all right, let's take this thing a little bit further. Because in aqueous solution, they're not together like we're listed here. They're broken up into their ionic components. So sodium chloride actually breaks into two ions in the water phase. Na plus and Cl minus. Okay? Now I could write aqueous under each one of these. It's kind of redundant and it's going to really wear out my poor little markers. So what I'm not going to do is represent aqueous here. Okay? So if you see an ion in any of my ionic equations, assume that it's going to be aqueous. If it's not aqueous, I'll indicate that it's not by representing the phase, gas, liquid, or solid, for that particular structure. Okay? So I'm going to do the same thing here with silver nitrate. Since I know it's aqueous, I'm going to break down silver and nitrate. What's the charge on silver there? Well, I know what the charge on nitrate is. Do you? It's -1, that's right. So this is a -1, okay? So if I've got one nitrate and it's a neutral molecule, what's the charge in the silver? +1. Very good. All right, so those are all of my ions. Now, when these things react in a solution, sometimes they get what's called a precipitate. What a precipitate is when things fall out of solution. So, wouldn't you know it, that this is one of those cases where that happens. What I do to try to find this precipitate is I do what's called a double replacement reaction, or metathesis. And I'm going to take these two, and I'm going to swap them. Okay? And if I swap those two, I'm going to look at the products that are generated. What I'm going to have is sodium nitrate. I'm writing this right now as aqueous. Actually, I'm going to write it up here. So sodium nitrate and silver chloride. All right. Now notice what I did up there is I wrote an S next to the silver chloride. This means a precipitation happens. So something happened, and to represent this with ions, I'm going to represent this as Na plus NO3 minus. Okay. And because silver chloride is a solid, I have to represent it with the ions together. Represent it as a solid. Okay? So what this is that this is a total ionic equation. So total ionic equation. It means I represent all ions in all phases. Okay? Now because I have this total ionic equation, I look at this and I say, well, how important are the sodium and nitrate in this case? Because I put these in the solution, and it doesn't really change from a sodium from the products to reactants to products. The same thing with the nitrate. Nothing really happens with it. They just stay in solution and hang around and watch. Okay? They just pull out their cell phones and start recording what's happening between the silver and the chloride. So when you have that case, okay, when you have two ions that don't really do anything, we tend to pull them out of solution. And we talk about net ionic equations. Okay? And for my net ionic equations, what I do is I eliminate anything that's just a spectator in the reaction. Because it's not really what's important as far as the story goes. So sodium and nitrate get dropped out of both sides. Because they appear on both sides as the same thing. It means nothing's happening to them. Right? but the silver and the chloride are important. So for a net ionic equation, and generally we start with cations, I get the silver, and I add that to the chlorine, and what I get out of this system is silver chloride solid. Okay? So that's my net ionic equation. Now I know what some of you are thinking, you're scratching your heads going, Dr. Wayne, that's amazing. How did you know that you would get silver chloride as a precipitate? Well, the answer is, I've done this in lab before, I kind of know the answer. Okay? But the real answer here is that there are rules that have to be followed for specific types of ions. Okay? So let's go ahead and look at those rules so we can define them so we can always predict what's going to happen as far as precipitation reactions go. So now we move into something called the solubility rules. What the solubility rules state is you kind of do this flow chart. When you do the flow chart and you identify things and find out if things are soluble or not. So you can always find out if a specific salt is going to be soluble or not. All right? So our first rule that we've got here is that all alkyl halides, no, excuse me, not alkyl halides. I've got organic on the brain, I'm sorry. All alkali metals and NH4 plus, known as ammonium, are soluble. Okay? So for all salts that contain alkali metals, we know that these things are going to be soluble. All right? So to give you an example, all right, I know that NaCl is going to be soluble in a solution. I know that potassium bromide is going to be soluble. I also know that sodium acetate is going to be soluble because it's got a sodium associated with it. Okay? All of those guys are going to be considered soluble, right? The second rule that we're going to work on is anything that contains the following two. So this is rule 2. And that's anything with nitrate and chlorates are soluble. So remember from the previous example that I had silver nitrate. And I know that's soluble because all nitrates are going to be soluble. Okay? So that's my second rule. All right? So if I'm running through a list, if I've got a material, all right? Any material that's got a chlorate or a nitrate, those are going to be considered soluble. And I forgot one, so let's throw that in. Nitrate, acetate, and chlorates are all going to be soluble. Okay? Which brings us to our next rule. And the next rule is that I've got compounds containing halides, chlorine, bromine, iodine. Okay? Now I'm going to write, does it contain Cl minus, Br minus, or I minus? Okay? And notice I put that in the form of a question. Now at this point, my flowchart can branch off into two different directions. And that is, if it contains but has silver, lead, or mercury, all of those are going to be considered insoluble, right? At this point, I've got exceptions, all right? So these ones here are insoluble. If it doesn't have any of those exceptions, then we know that it's going to be soluble, right? Okay, so it's soluble at that point. Let me move this over a little bit. And soluble means that it dissolves in water. Okay? If I get a no, then I go to my next question. All right? Does this contain a sulfate? Okay? If it contains a sulfate, I'm just going to write the word sulfate here because I'm running out of room. Sulfate, that's SO4 minus 2, question mark. Is it yes or is it no? But at this point, I'm going to have yes, but notice this is the insoluble area. I've got exceptions to this rule. And the exceptions are going to be silver, lead, mercury, and barium, strontium, and calcium. But these last two, it depends on who you talk to. Because sometimes they're listed and sometimes they're not. But these are going to be considered insoluble as well. All right? Notice here that these top three, silver, lead, and mercury, appear up on the top as well. All right? If I have a yes and don't have any of those cations associated with it, you betcha it's going to be soluble. All right. So far so good. We've got almost all of them here. All right. Everything else is basically going to be insoluble. All right. So this is the solubility chart. So if I get a no down here, I'm probably going to run into something that's insoluble. Now these are guidelines, there's exceptions to everything. This is where I run into the exceptions over here. All right? But essentially, once I get past sulfate, I start running into insoluble things. The only times that those insoluble things are soluble is when they match these particular rules, which is why we start with the soluble rules and not the insoluble rules. Okay? So let's go through some examples. All right, so here I have some examples on the board. So let's go through them. Start up here, sodium carbonate. All right? You go through the rules, and right away we've got a hit. And that hit is that we've got a sodium. Sodium indicates that we've got something that's soluble. All right? So this is my first rule. My first rule says if anything I've got a sodium, sodium is going to be soluble. So this thing is going to be considered aqueous. Okay? Right. What about ammonium phosphate? Well, if you remember the first rule from the previous part of the video, ammonium, NH4 plus, is one of those soluble ions as well. So I got a hit on my first table, I got my first bubble on the flow chart, and that's going to be an aqueous system as well. Now what over here? Magnesium acetate. At this point I've got a hit on the second bubble, right? And this salt says anything that's a nitrate, chlorate, or acetate is going to be considered aqueous. I forgot to put a 2 here, so let me put a 2 here. So because this thing hits on my second bubble, I'm going to be considering this to be aqueous. Now I drop down to the sulfates. Okay? Sulfates, I run into my fourth bubble, and I have to look for exceptions for sulfates. And one of those exceptions is lead 2 plus. Is this lead 2 plus or is this lead 4 plus? Well, sulfate is minus 2. Okay? That means that lead is plus 2. So, whammy. That means I've run into an exception. Let me use a different color here so you can see the exceptions. So this one is going to be a salt. A precipitate in a reaction. It's not going to dissolve in water. Barium sulfate. Barium can only be a plus 2 because it's an alkali earth metal. And we know that sulfate's minus 2. We look at sulfate, because we're on that bubble, fourth bubble, and sure enough, barium is an exception to that. But what about nickel sulfate? We look at nickel sulfate, another fourth bubble sulfate. Is nickel an exception? This is nickel plus 2. Guess what? Nickel's not on that list, which makes this an aqueous system. What about aluminum carbonate? Now at this point, we kind of run into a problem because we've run through all of our bubbles. We get down to the bottom, we're like, uh-oh, must be insoluble. Does it have anything that's an exception there? Aluminum doesn't show up as an exception. Carbonate is not on the soluble list. As a result, aluminum carbonate has got to be considered a precipitate or a solvent. So if I dump that into water, nothing happens. No, nothing happens, okay? So that's how we run through these ionic equations. Those are some examples. And I encourage you to find a source of problems, run through these, and see if you can identify what's soluble and what's not. Because once you do that type of analysis, you'll be able to determine a lot easier looking at these things. You'll get used to that entire table and identify what's soluble and what's not.